So in order to get stuff to line up on a map, different pieces of data on top of each other, we have to use a coordinate system. But the issue is that the actual Earth is a really lumpy object. It's got topography and bathymetry, and even the ocean height, sea level, which to us seems like, oh, well, that's the shape of the Earth, is the ocean. Well, even that changes based on, whether it's tides or different weather systems or things like that. There's different pressure. So there's a whole field of study, luckily, called geodesy, and there's Earth scientists that go out and try to measure the Earth. What they find is that the acceleration of gravity is actually different at different places on the Earth, which means that the mass of the Earth is not spherical. It's not even close. It's what they call a geoid. It's a geophysical approximation of the Earth. And I think the kind of easier way to understand it is that if the entire surface of the Earth were kind of a liquid and there were no wind or tides, but only the gravitational field and the rotation of the Earth were taken into account, what is the shape that Earth would take? But lucky for us, we don't actually have to deal with that, because as cartographers and GIS practitioners, we still need a grid system. So the geoid isn't good enough because it's lumpy. We need a clean mathematical object, like an ellipsoid, to assign values of latitude and longitude so that we can actually locate things on the Earth. So the latitude, hopefully, as you know, it climbs like a ladder, like this. It measures how high we are off of kind of 0 at the equator, 90 at the poles, and we'd say plus 90 and negative 90. Negative 90 being the South Pole, plus 90 being the North Pole. And latitude and longitude are kind of great because we're like, okay, well, if we have this system, we can always know on this ellipsoid, it's really an oblate ellipsoid, it's kind of just this squat egg-shaped thing, where we are anywhere on it using the system. So the problem with the ellipsoid is that it doesn't really, we can't measure with it. So if you can see right here, if we were to keep going north and north and north, and we were to actually measure using latitude, it's consistent. Latitude, 1 minute of latitude is a nautical mile at the North Pole all the way to the equator to the South Pole. But longitude, the one that measures kind of east-west direction, it starts at the equator as 1 nautical mile for every minute. But as you go north and south away from the equator, it kind of gets skinnier and skinnier and skinnier. And then suddenly, it's at the North Pole exactly, it's 0. There is no measurement for longitude at the North Pole. So the problem is when our units kind of vary, so the degrees of longitude are not constant, we can't reliably measure, I should say, any kind of area or distance or anything like that. So what do? We've just figured out, okay, we know how to locate things on the globe, but we can't measure anything. So the next thing we do is we make a planar coordinate system, a Cartesian coordinate system, just X and Y. And if we can get from here to here, then that means that we can actually measure, okay, this is 2 feet, and that's 2 feet. 2 times 2 is 4. That's 4 square feet, right? We can actually make measurements in a plane, whereas when we're on an ellipse, it's very difficult to easily make measurements. First, let's just talk about the second major problem, and that's that the ellipsoid doesn't exactly fit the geoid either. We're trying to make them work together, but there's more than one way we could fit this ellipsoid to the geoid, and depending on how we fit it, we're probably going to have to make some sacrifices. Okay, maybe we can get it to fit pretty well so that Europe here, Europe is all very close to this surface, but then this is going to be like kind of a big divot underneath maybe the other side of the surface. So what we've got are something called datums, and geodetic datums are the way we use the ellipsoid to try to fit the geoid. There are lots of datums, but we're not going to be that worried about it. In general, we only use 2 datums, and this is all you should really worry about in terms of geographic coordinate systems. And the 2 datums that we use are WGS 84, which tries to fit the entire world okay, as best as it can, and it stands for the World Geodetic System and it was done in 1984. The only other one that you'll encounter a lot is NAD83, and that's a different ellipsoid, a different datum that tries to fit North America as best as it can. And so it's a little bit more accurate for North America than WGS84 is, but it's called the North American datum, and it was done in 1983. So it's important to know about datums and that this is, these are geographic coordinate systems, but we're really only going to use two for the whole intro, this whole course. And those two are WGS84, which if we ever do anything outside of North America, we will use, and NAD83. So now that we've gone from the geoid, we've decided we're going to use one of these two datums, these geodetic datums. But now we want to measure something, and how do we do that? Well, we have to go from ellipsoid to planar. And so in order to do that, we have to do something called a projection. And you might think in your mind, oh gosh, this sounds terrible. And it can be. It's really tricky because whenever you take a curved surface and try to flatten it, you're going to get distortion no matter what. And that's a few weeks away still. Choosing projections is a huge part of kind of managing your analysis and managing any measurement you do, and also can really greatly affect how people interpret your map. So projecting from a geographic to a projected coordinate system, or kind of this ellipsoidal to this planar coordinate system, it is a big deal. But for now, let's just remember that geographic coordinate systems, these are always in degrees, right? Planar coordinate systems are either in feet or meters or kilometers or miles. They're always in kind of a unit that has an actual measurement. For now, just remember that projections are flat and that they are planar coordinate systems, and there are three types. You can use a plane, a cylinder, or a cone. Planar, also called azimuthal, cylindrical, or conic projections, all are versions of how do we get this curved surface to a plane. So don't get too bent out of shape just yet. Just remember that we've got the crazy Earth over here, different, all these different problems that we have to figure out. Very smart people help us out. They give us a geoid, but really we just have to choose what geodetic datum or ellipsoid we want to use. And once we do that, our entire job is mostly choosing how we project our geographic coordinate system. So if this is confusing, watch it a few times and we'll talk about it as the weeks progress.